And now what do you do with transitive closure? Let's look at transitive closure. So here we are not worried about the distances, right? We are only bothered about whether there is a connection or not, right? So you can start by setting up this matrix Aij, let's call it Aij star, right? Some initial matrix. Instead of working with the adjacency matrix, we'll work with some other matrix called Aij star. What is this? We'll set it to infinity. An entry Ij of this matrix, we'll set it to infinity if Wij does not belong to E. Yeah. And if Wij belongs to E, right, if it's an edge in the graph, then I'm going to set it to 1. Okay. Is that clear? So essentially all I'm saying is that I'm just trying to keep track of whether I'm connected or not, right? If I can reach J from I just say that it's connected. And 1 just indicates it's connected, infinity indicates it's not connected. That's all, right? There's one more thing I have to take care of over here. Because we are looking at connectivity, I will also set it to 1 if I is equal to J, right? I may not have a self loop, but I still want to set that to 1. I'll always assume that everybody is connected to itself. Okay. All right. Now what am I going to do? Well, let's look at our notation, right? What were we using this for? Dij. So now I have my D0, which is set up as basically A star ij, right? Same as before. So let's say I have computed all the way to dk minus 1. So what is the notation dk minus 1? Or what is pk minus 1 ij? Pk ij. What is pk ij in this case? It basically says if there is a path, this is equal to 1. If there is a path from I to j that only comprises of v1, v2 all the way to vk as intermediate vertices. Is that clear? So now we are not interested in the distance, the length of the path and so on, right? We are just interested in whether or not there is a path. So, okay, I shouldn't say this equal to 1. This is a path, right? Pijk is a path from I to j that only comprises of v1 through vk as intermediate vertices, right? So this d, what am I using this dijk for? This is basically 1 if pijk path exists, right? And infinity if it does not exist. And also if path exists or itself, right? Self loops, that's what we did for I equal to j, right? If it's self-connected. Okay, is that clear? So now how do you update dijk? Let's see. What is my dijk going to be? Either my path, which comprises of vertices from v1 through vk, either in that intermediate path vk appears or it doesn't appear, right? First, let's take the case where it doesn't appear. In that case, what is your dijk? In that case, dijk will be simply dij k minus 1. Is that correct? There was already a path, so dij k minus 1 must have been 1. Yeah?
Yes, sir.
Okay. And now if vk is in the path, right, then you can break the path into 2 parts, one from I to k and the other from k to j, right, as before. So there will be a path from I to k comprising only of vertices coming from the set v1 through vk minus 1. And similarly, there will be a path from vk to vj, right, comprising of vertices coming from the set v1 through vk minus 1. What do I need to do? I just need to check if there is a path from I to k, dik, comprising of these vertices, and there is a path dkj comprising of those vertices. So since we are using AND operation, it's easier. Instead of using 1 and infinity, let's just use true and false, right? So let's set dij k to true if pijk path exists or if the two vertices are the same, I is j, right? And let's set it to false if it does not exist. Yeah. So then we can work with logical operators. So now what is dijk? Well, if there is a path from I to k and from k to j, right, comprising of only vertices from v1 through vk minus 1, then dijk should be true. Otherwise, if there already exists a path from vi to vj, comprising only of vertices from v1 through vk minus 1. Yeah, so what operator do I need outside here instead of min?
Or.
Or, right? I'll just use an or operator here. If either of these is met, I have a path from I to j comprising of vertices from v1 through vk. Clear, guys? So that's it. That's the algorithm for transitive closure. You just reuse Floyd's algorithm. Now, again, there are other algorithms, more complicated. If you ever have to solve this problem, at least these basics should be clear. If you have to solve this problem, you can always read through them, right? So you can get better efficiency than what is reported here, right? For practical purposes, it doesn't matter so much. There are again heuristics. So those algorithms help for different reasons, right? There are algorithms which reduce the constants. So here we are not worried about constants. We are only looking at asymptotic isoefficiency. But actually constants in real life really matter. We aren't touching upon those right now, but you can always look into those. Okay, any questions?
So, I mean, the algorithm is still order V cube, right? And let's say,
Yes.
even if I naively ran TFS V times for each starting vertex, then the complexity would be order VE. I mean, that would be, better if, let's say, it is a sparse graph.
Now, how do you parallelize it if you have P processors?
Yeah, I mean, that's a different question, but I mean, do we have algorithms that work on, let's say, not on this Floyd's algorithm, but others, uh, which could, let's say, be better for sparse graphs?
So we'll cover depth first search in parallel. So you can come to know how you can use that if you want to use DFS for solving this problem, right?
Okay.